All right, we are back, and I have my pen working again, so I am happy. It was just a dead battery. Just took me a minute to go find them. Nobody sells these quad A batteries hardly anywhere. You have to look specifically for them. Did finally find them in Fred Meyer in their electronics section, so yay, that's fixed. All right, so picking up where we left off, the last part we were talking about was the things to remember on our introduction of these guys. Okay, so we have to remember that our capacitive reactance is found by using the formula 1 over 2 pi Fc. The inductive reactance is solved by finding 2 pi Fl. So remember, in a capacitor, as the frequency goes up, the reactance value goes down. As the opposite in an inductor, as frequency goes up, the X of L goes up as well. And our critical frequency, we're finding that when the resistance value equals the reactance value. Our resonant frequency is when our X of L is equal to X of C. We can find the decibels in two methods using power or voltage of the output compared to the input. So if we're using power, we use the formula 10 log times the power out over power in, or to use for voltage, we take 20 log of the output over the input voltage. And the last little note that we have at our critical frequency, that is one of our 3D points, half power point, 0.707 of volts peak. That's the idea that we're looking for this critical frequency. This is kind of the limit that we're considering as good, that we want the data, or bad if it falls below it, that we're going to reject. So with that being the case, let's go ahead and kind of continue on, and let's learn more about the actual filter types themselves and how to use them. So keeping all the rest of those things in mind. So the first thing we're going to talk about is we're going to be talking about RC filters, so resistor capacitor filters. So the idea behind them is basically, like I was saying before, it's now the position matters. So it matters if we have our capacitor first, our resistor second, and it also matters where we're taking our output off of in that configuration. So we have two types of filters, or two different configurations that we can kind of look at as very basic in RC filters as we can get. So we have our circuit, and in this instance we have our resistor first and we have our capacitor second. And across the capacitor we're taking our V out. The other one we want to look at and kind of compare against these guys is when we have our capacitor first and we have our resistor second, with the voltage out being, with our output being taken across the resistor itself. So in this instance, we're going to go ahead and apply some values to this, and we're going to go through and solve it. So, one thing to think about is what is happening in the circuit. So as we are sweeping our frequency from 0 up to 2 meg, for example, or 20 meg, or whatever it is that we want to do, what's going to be happening with each of these parameters? Okay, so remember, our X of C is going to go down when our frequency goes up. And that's going to be true in both these situations. So in this instance, if we look at it, if we start at a low frequency, we're going to get a very, very high X of C value, which is going to take a larger and larger portion of the total voltage. When the frequency gets higher and higher, this X of C value gets lower and lower. So eventually what's going to happen is this capacitor here is going to be dropping less and less voltage across our output. So hopefully you guys can kind of start to see this trend of what was filtering out essentially. So in this case, we have high values of reactance at low frequencies, which means we have a higher voltage. So when X of C is higher, the voltage drop across it's higher, and inversely too. And we have a low reactance value, we're going to have a high or a low voltage drop. And both these are going to be going on simultaneously, or not simultaneously. Both of these are happening on the same circuits. As we go up and down, and just like I said, it matters where do we take our output off of. So let's go ahead and figure out which circuit is which. Thinking about some of this information that we just talked about. Remember these relationships. That's kind of the whole idea behind this. So we're going to figure this guy out. What we're going to do is we want to write out a couple of tables to gather all the data between these 2 points. So what we're going to do is we're going to create a data table to kind of go through here and determine what are our properties, what is, what's our voltages out, what is our dBs, what's our currents, what's that kind of stuff. So here we have 15 kilo ohm resistor on both sides, and we have 179 picofarad capacitor. So using this information, we're going to sweep the frequency, we're going to calculate it at several different points, and then we're going to find out at the very end what is actually our critical frequency, and then what type of filter is this. So the first types of filters we're going to deal with between RC and RL are going to be high pass or low pass. Those are the only two options that we have, and so we have to make the determination of which filter is which. So looking at this guy, we're going to set up our table. And it's going to look something like this. We're going to have our frequency at which we're going to calculate all these guys. We're going to have a resistance value at each of these set points. We're going to have an X of C value at each of these set points. We're going to have a current total at each of these set points. And then we want to find out what is the voltage out when it's across our capacitor. What is the dB of our output? What's the decibels? Then we want to also find what's the voltage out for our resistor when we use that as our output. And again, what is our decibels on the output? And that last column I don't believe we are going to use, so we'll just kind of leave it blank. The frequencies that we want to use, we want to, we don't want to over analyze these circuits, but we want to have a pretty good idea of what's going on. So we're going to break this up. We're going to do 4 frequency ranges. Apparently I make my charts way too big. So we'll just change this real quick. One, 2, 3, 4, and then we'll split these guys up. So I'll kind of be bouncing back and forth between these two, between our chart that we'll fill in and then the supporting math that we'll do below it. So the frequencies I want to look at, just label this one as ohms, this one is ohms, this one we're going to label as amps, the V out we're going to label as volts, decibels will be in dB, and then we got volts and dB again. Okay, so we want to run at 60 hertz, we want to run at 6,000 hertz, we want to run at 600,000 hertz, and we want to run at 60 megahertz. It's kind of a good range across the full spectrum of frequencies that we could be dealing with. So let's go ahead and get into the math to this circuit. And as we go, like I said, we'll come back through and we'll fill in the tables as we go. I have these kind of broken up, so we're solving for all of one value at a time. We're going to solve for all the resistance values, solve for all the reactance values, all the currents, voltages, decibels, and things like that at each of the different frequencies. And then we'll kind of talk about what we're looking at when it's all said and done. So the other way you can go through is you can just go through each line at a time. Do 60 hertz, what's going on, 6,000 hertz, what's going on, 60K. And we can do that too. I might have to just change my notes up, so it'll take me just a hair longer to get the information. But we can go ahead and go through that. So maybe that's what I'll do. I think that'll be easier. We'll just go through this one frequency at a range at a time. So that way we're not screwing anything up and we know what we're doing. And then we can kind of see these trends evolve. Okay, so the first thing we're going to do is I will start with the 60 hertz. So my frequency is equal to 60 hertz. And my base circuit that I have is this guy. And we have an input voltage of 5 volts peak. Okay, so here is my base circuit, and I will color code these to kind of coordinate with the different frequencies. So 60 hertz is going to be in red. So the first thing we need to look at on our chart is resistance. Now, is a resistor affected by current at all, or by the frequency at all? No, it is not. So the nice thing here is the resistance is going to stay the same for every single circuit. So we can just fill that in now since nothing's going to change. So now that we have that value, let's continue on with our 60 hertz. We need to find what the reactive capacitance, or the capacitive reactance, sorry, of this capacitor is at 60 hertz. So remember, x of c is equal to 1 over 2 pi times the frequency times the capacitance. So x of c is equal to 1 over 2 pi times 60 hertz times 176 picofarads. That value comes out to be 15.071 mega ohms. Okay, so let's come back up to our chart and let's add that in. So our x of c value is 15.071 meg. Now, one thing that we did not include on here was our total impedance of the circuit, and I probably should have added that to our chart. Let me just look through my notes real quick. I did not include it on any of my charts, so we'll just we won't add it in there right now, but we know we can still get it, and it'll be in our notes for next time. So we won't worry about recording it on the chart, but just understand that we still have to find that. So now that we have this reactance, and remember this is at a negative 90 because it is a capacitor, so now we need to find the impedance total of this entire circuit. So we take our 15,000 ohms, which is our real value, minus J of this 15.071 meg, and we know it's negative J because it's at negative 90, so those negative signs are going to translate. We have that value. We need to convert this guy into polar because we're going to be doing division with it, and it comes out to be 15.071 meg at an angle of negative 89.316 degrees. Now that makes sense too, because remember, our reactance value is so much larger than our 15 kilo ohms for the resistor that we're going to be approaching the full negative 90 degrees of this guy. It's going to affect it a little bit, but not much. So now that we have that, let's solve for our current totals. Because then once we have our current, we can find the voltage drops across these guys. So remember, current total is equal to the voltage total divided by the impedance total, which we just found. So we have 5 volts peak. We're going to divide this by the 15.071 meg at negative 89.316. So when we do that, that comes out to be 331.763 nanoamps at an angle of 89.316 degrees. Really small current. So let's add this up to our chart here so we can keep track of it. So 331.736 nanoamps at an angle of 89.943 degrees. So now with that, we need to solve for the voltage drop across our capacitor. V out of the cap is equal to the current total times the reactance of the capacitor. So we take 331.763 nanoamps at the angle of 89.316 degrees Okay. Oops, sorry. I wrote this current wrong. It's 89. No, I did that right. 316. All right. So now we go back to our voltage. So 331.736 nanoamps at this angle. And we're going to multiply that by our reactance, which remember was 15.071 meg at negative 90. So this is going to come out to be, so I'm just going to put V out across the capacitor, just shorten it down, is going to be equal to 5.000 volts. Now, for these next little bits, I don't really care what the angle is right now. We can go ahead and find it, but honestly, that's not what my focus is on these guys. I don't care what the angle is, to be flat out honest. We need to understand that it's still there and we can calculate it. At least for these circuits, all I'm looking for is just the magnitude of the value. So from going forward with these, you'll kind of see I dropped the angles off of them. They're still there. They still all are applicable, and they will matter, when we're solving for the first parts. For this voltage, all we're really caring about right off the bat is what is my peak voltage across each of these components. So the voltage out across my capacitor is this value, is 5 volts. So right now we can see we're sitting at 5 volts at 60 hertz. The other thing we can do is when we look at the circuit, even if we were to come back up here and look, between these two guys, the only difference is what are we looking at for our output? We've switched these positions, but we can calculate these both at the exact same time because it is the same circuit. Everything's connected in the same way. It's just where's our output going? So if we were to look at this guy, even with the same circuit we're working on here with this first one, is if we were just to switch this and shift our output over to R1 or change our ground or whatever, that's really what we're doing. So we don't even have to redraw it. We can get the current and we can solve the voltage drops across each of these guys just like we've done before, but now we're actually taking an interest in where the output is coming from. And like I said, we'll talk about these once we get this chart filled in. So the voltage we have across our capacitor is 5.000 volts. Now the reason I'm including the 3 zeros is because that's what my calculator spit it out. It rounded off the value and it gave me the 3 decimal points of what I wanted. So that's where we're at now. So we have that voltage across our capacitor. We'll solve, so now that we have that, one thing that we need to look at is, okay, so we have the output. Let's find out what our decibels of the signal is. Okay, we have voltages. We don't necessarily need to go through with power, so we can just take the 20 log of our output over our Vin. So V out over Vin. We run that through. V out over Vn is 5 over 5, which gives us 1. 20 log of 1. So let's run that through. So we got 20 log of 5 volts. And our in was 5 volts. That gives us a dB gain of 0. So basically what this is saying here is we have no loss, but we also have no gain. So what we're putting in is exactly what we're getting out. And that's what we should see when we have 5 volts in, 5 volts out. We should have a 0 decibel is our value for this. So now while we're here, let's also solve for the voltage across the resistor as if we were taking the output of it, like we have in the second circuit over here. If this is how we were taking our output, we can calculate that voltage and we can use these same steps. So when we want to do that, so the voltage out across our resistor is equal to the current total times the resistance value. So the voltage out of our resistor is equal to 331.763 nanoamps. We're going to multiply that by our resistor, which is 15K. So now the voltage out of our resistor is equal to 4.976 millivolts. And then the dB is going to be equal to 20 log times the V out, which in this case is across this resistor. So we put the 4.976 milli divided by the 5. And so in the circuit, our dBs for this guy comes out to be negative 60.042. So basically what this is saying and what this translates to is we have a 60 decibel loss of voltage in this circuit. So we're losing that much voltage compared to what we're putting in. So like I said, we'll discuss what this means. We'll kind of chart it out and we'll show you guys in graphical form so you can see what this is doing. And these are the things you're going to measure. This is another way to say, hey, I'm losing voltage or I'm not getting as much voltage out as I'm putting in. And like I said, they're all going to be negative with the exception of being 0 because you're going to have some loss because the voltage is going to split up between each of the two components just like normal, but together they add up to the sum of the total coming in. So you got to remember that that's where it's coming from. We're always going to have some sort of a loss because the different components are going to be dropping different voltages. So let's go ahead and put these up here. So we have a minus 60. Get to my notes, 60.042 decibels, and then the voltage out we had was 4.976 milli. Okay, so now that we have those, that is everything that we need to do for this first circuit, or for our first frequency. We've gone through and calculated everything. So now let's go ahead and we'll just indicate that this one is red in color. So now I'm going to switch to green and we're going to solve using our frequency of 6K. So we're going to do everything we just did with a different frequency and we're going to see how things change. So now we've increased our frequency by 10 times. Or is it by 100 times? 60, 100. We've increased it by 100 times. So essentially we've gone up 2 decades. So now we have the same circuit because we didn't change anything about that. We have 176 picofarads. We have 15 kilo ohms of resistance. And only this time we have 5 volts peak, and this time we have 6 kilohertz for our frequency. So when we come here and look, this is all going to be changing. Our X of C's will change, our impedance will change, the current will change, and the voltage drops are going to change. Okay? So the first thing we need to do is solve for our X of C1 at 6 kilohertz. So remember, 1 over 2 pi times the frequency times the capacitance. So X of C1 is equal to 1 over 2 pi times 6,000 times 176 pico. The reactance that we get out of this guy is going to be equal to 150.715 kilo ohms at negative 90. So I'm going to do the math to find the currents so we can find the angle of those. But like I said, after that, once we look at the voltages, we don't necessarily need it. And for this example, we don't care about it. But I want you guys to be able to continue to see these angles as they change based on the frequencies. That's going to be one of the points that you guys see with the angle of the currents as we get going. All right, so now that we have that value, we have our X of C1, we need to find our Z total, the total impedance of the circuit. What is this 5 volt signal seeing? So it has the 15 kilo ohm resistor, and then we have the 150K impedance of the capacitor. So again, we're going to want to convert this into polar because we're going to be multiplying and dividing it. So what we get is 151.46 kilo ohms at an angle of negative 5.737 degrees. Nope, I jumped again. That's the next one. 84.316. So now, and I think I screwed that one up here. I did, but that's not going to matter. This guy up here, this should be 89.943 degrees. So that's going to change all those values when we solve for the currents and everything. But just know that it's still fairly close to 90 degrees based on the capacitor because the capacitor is so much larger than the resistor. So I apologize for that. It's not going to make that much of a difference on our math. So as we go through here, this is what we end up with our total impedance. It's 151,000 ohms versus earlier where we had 15 mega ohms. And again, the angle is still very high, close to 90 degrees, because this capacitive reactance value is so much larger than our resistance. It's still going to drop the majority of it. So we end up with this value, 151.46 K at an angle of negative 84.316. And so now we want to find the current total. So it is a voltage total divided by the impedance total. So we have 5 volts peak, and we have 151.46 K at an angle of 84.316. So the current total for this circuit is equal to 33.012 microamps at an angle of 84.316. Okay, so now that we have those, we have a current. Let's go ahead and add those back up into our chart to keep track of them. So the reactance value we had is 150.715 K. The current total that we had was 33.012 microamps. And so now we need to solve for the voltages and what our decibel ratio is for each of these capacitor and for the resistor. So the voltage out for the capacitor is equal to the current total times the reactance of the capacitor. So 33.012 microamps. And our reactance we had is 150.715 kiloohms. So V out of the capacitor is equal to 4.975 volts. And then we want to solve for the voltage out for if we're using our resistor. It's going to be the same current multiplied by the resistance instead. So 33.012 microamps multiplied by the 15K. So the voltage out of our resistor is equal to 495.18 millivolts. Okay, so now we're going to go ahead and we'll calculate the decibels of these guys. So the decibels of our V out across the capacitor is 20 log times the V out over our V in. So 20 log of 4.975 over 5. The voltage out decibels so we end up with a negative 43.538 milladecibels. So very, 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 very small change in what we've lost a little bit. So very, very small ratio. That's the idea behind these. We're just looking, it's a quick comparison that we could use that now can compare the voltage drops against each one of these as if they were, the same thing. This is dropping down this far, this is dropping down this far. So we have our decibels for the V out for the resistor is equal to the 495.18 milli divided by our 5 volts. And this is the 20 log of our V out over V in. Got ahead of myself there. So the decibels for a V out of the resistor is 20 log times 495.18 millivolts. We divide that by 5. And that value comes out to be negative 20.084 dB. Okay, so let's go put those values into our table. So up here, so we got negative 40, negative 20, 0.084 decibels with a voltage drop of 0.495 volts. So I'm just kind of shifting this a little bit to show the difference between the values of these. So on this one would become 0.004 volts. And the voltage out for our capacitor is 4.975 volts. And the dB drop is a negative 43. I'll just put this in terms, so negative 0.043 dB. That way everything we're looking at we can compare it to the same values. All right, so now that we have our next one done, we have our 6,000 ohm hertz frequency, or 6,000 hertz frequency. Now we want to do it for two more times. So we want to do it for 600,000 hertz and the 60 megahertz. So we'll do this in here. This next one's going to be our purple color. So again, we're just working the same problem with different frequencies. We're not doing anything special. (176 picofarads with 15 kilo ohms. And this time we are running at 600 kilohertz with a 5 volt peak signal. All right, so we need to find the capacitive reactance. So our X of C, again, 1 over 2 pi FC. So the reactance that we get is 1 over 2 pi times 600,000 hertz times the 176 picofarads. The capacitive reactance for this guy comes out to be So we have 1.507 kilo ohms at negative 90. So now we want to go through, find the impedance total of this entire circuit. So we have our 15,000 ohms minus J of 1.507K. We're going to take this value, convert it to polar. And with that, we end up with 15,076. So 15,076 ohms at an angle of negative 5.737 degrees. So if we look just in noting what we've had before, so when we went from the 6,000 hertz to the 600,000 hertz, we completely shifted to where now this is starting to approach our zero value. And as we can see, that makes sense because our resistance value is now a lot larger than our capacitance value is. So we see this value as it's going, as the frequency is going up, this X of C is getting smaller and smaller and smaller, which means it's going to be having less and less effect on our entire circuit, which we can see by the phase angle of the impedance. So now let's get into our current total. So we're going to take the voltage total divided by the impedance total. So we take 5 volts at our 0 and we divide it by the 15,076 at negative 5.37 degrees. And their current total we get out of this guy comes up to be 331.653 microamps at an angle of 5.37, 737, sorry. So there is our current, and there is our capacitive reactance. Those are the big things we want to look out for. So let's add them to our chart. So the X of C value is 1.507 kilohertz. Our current total is 331.653 microamps. Now we just need to solve for our voltages. So the voltage out across our capacitor is going to be equal to the current total times the capacitive reactance. So we get 331.653 microamps multiplied by the reactance, which is 1.507 K. And that gives us a voltage drop of 499.801 millivolts. The decibels of this guy, so we take 20 log of our V out over our V in. So the decibels value we end up with is 20 log of the 499.801 milli divided by 5. So the decibels for the voltage out on across the capacitor comes up to be a negative 20.003 decibels. So remember, our decibels is just literally our ratio of our output to our input. So now we want to find our V out with our resistor being used as the output. So we take the current total multiplied by the resistance. So we have 331.653 microamps. That's going to be multiplied times 15,000. So our V out across the resistor comes up to be 4.975 volts. And then we want to solve for the dB of this value, the ratio. So we take 20 log times the V out over V in. Now remember, between these two, we've shifted where our V out is taken from. In the first one, the V out is taken across our capacitor. The second one, the output is taken across the resistor. So now we have dB is equal to 20 log of 4.975 at 5. And this decibels is equal to negative 43.538 decibels, millidecibels. Okay, so let's add these values back up to our chart. So the voltage out across our capacitor is going to be 0.500, because if we round the 4.99.8, that comes up to the 5. And the decibels for it was negative 20.003. The voltage out for the resistor was 4.975, and that gave us a negative 0.0444 decibels. Okay, now that we have those done, we have one final circuit to do, and we want to do this with our with the last value that we have. We'll do this one in kind of a gold, and this is the 60 megahertz for our frequency. So when we get through this, again, we're going to have the exact same circuit. Do this. We have our resistor, we have our capacitor, we have 176 picofarads, we have our 15 kilo ohms. Okay. Yeah. Yeah, that's important to get. All right, so now that we have this value, we're going to do for the last frequency. So we're going to use 60 meg, and we're going to have 5 volts. We got 15 kilo ohm resistor here, and 176 picofarads. So again, X of C, 1 over 2 pi times the frequency times our capacitor. So our X of C is going to be equal to 1 over 2 pi times the frequency is 60 meg times the capacitance, which is 176 pico. The reactance that we have across this guy is 15.07 ohms. We want to solve for the impedance of the whole circuit. And as I'm pulling my notes up, give me just a second, I dropped them. Okay, so we have our 15 kiloohms minus J of 15.07 ohms for our reactance. We want to convert that into polar. So after we do that, it's going to be 15,000 at an angle of negative 0.058. So 58 milledegrees is what it comes out to be. So very, very, very teeny, teeny, tiny. I total is equal to the voltage total divided by the impedance total. So 5 volts divided by 15,000 gives us 333.333 microamps at an angle of essentially 0. You know, that is not much of an angle. We're never going to see that value on our scope. Never. We'll never see that. The lines will be way too, you know, that's going to be lost in the noise. So that's one good thing here. Like I said, we're not too worried about that value. So we have our current. Now that we have our current, we want to solve for the voltage drops across these guys. So the voltage drop on the output with using it as our capacitor is equal to the current total times our X of C. So we have 333.333 micro. We're going to multiply that by our X of C, which is 15.07 ohms. So the V out that we get across the capacitor is going to be equal to 0.005 volts, 5 millivolts. That's all it's going to be seen across this guy. Now we want to know what this is in dBs, so we can compare everything together. And 20 log times V out over V in. The decibels that we have is minus 59.96. So pretty much a negative 60 dB drop on our capacitor at this point. So now when we want to look, so basically what we're saying was we're negative 60 dBs. That means we are so little in our output, it's next to nothing. We can barely register it. We can't get much lower than that, maybe 61, 62 dBs if we keep going, but we're not going to worry about that much. So now the V out for the resistor is going to be equal to the current total times the resistance. So V out is equal to 333.333 microamps multiplied by 15,000. So our voltage drop is equal to essentially 5 volts. The decibels for this guy, and I can tell you right now it's going to be 0, but I'll show you the math. So 20 log of 5 over 5, V out over V in. Okay, so now that we have those values, let's go ahead and plug everything back into our chart and let's talk about it for a second. So we come back up here. The reactance we have was 15.07 ohms. The current total was 333.333 micro. The V out across our capacitor was 0.005. The dB was negative 59.96. The voltage out was on a resistor was 5.00 volts with an output of 0. So now that we have these values, let's take a look at what they mean. Okay, so we basically just went through a frequency sweep. We were running our generator from 0 hertz all the way up and past 60 meg, and we wanted to see what our circuit was doing. Well, now what we've done is we've kind of created a table that we can now plot to kind of see what was our response based on each of these values. Okay, so the next thing we're gonna do is we're gonna graph this information, and we're gonna have frequency on the bottom, and we're gonna have voltage or amplitude on our vertical. So horizontal will be frequency, vertical will be our output, the voltage drop that we have across that component. And now we're going to see what's going to happen based on the data that we got. So first thing we want to do is, and I'm going to slide this over to the side just so we can kind of go back and forth. So we have our graph, and actually I'm going to do this one in black. So we have our frequency. We're starting at 0 hertz here. We're going to have 60. We're going to have 6K. We're going to have 60 or 600K. We're going to have 6 meg, 60 meg. Okay, and then we've got 1 volt, 2 volt, 3 volt, 4 volt, 5 volt. So we got 1, 2, 3, 4, 5. We're going to designate these as volts. We're going to designate these as hertz. All right, so when we look, we're going to do these in 2 different colors. So I'm going to do, and I will write my legend down here. So the red dots, those are going to be with our voltage out across the capacitor. Okay, I'm going to do purple as the voltage out across our resistor. And we'll kind of see where these guys overlap. Okay, so the first one we have is at 60 hertz for our, I'll just do our resistor since I can see it on my screen right now. So we're at purple. So remember, this was 60 hertz, this was 6,000 hertz, this was 600,000 hertz, and this was 60 meg. So at 60 hertz, the voltage of our resistor was 0.004. So pretty much down here touching the line. At 6,000 hertz, it was at just under a half a volt. At 60K, it was at 4.95 volts. So we take this guy, we'll come almost to there, and then at 60 meg, it was at 5 volts. So what we've created is, if we graph these guys together, it's kind of a waveform that looks like this and then flattens off. Okay, so that's what this guy looks like. Now, I guess we'll zoom that out just a little bit. We'll get our information for our voltage of our capacitor. So I'll switch over to the red. So at 60 hertz, we had 5 volts. At 6,000 hertz, we had just about 5 volts, just slightly less. At 600,000 hertz, we had half a volt. And at 60 meg, we were pretty much at 0. So if we look at this guy, our curve goes like this. Okay, so looking at this, we can see 2 trends based on our output. So remember, if we want to look at things, we want to look at places that's going to give us higher than the 0.707. Okay, so let's just add that into our equation now. So when we have 5 volts, we're looking so about 3.5 volts. I'm going to do this in gold just to kind of demonstrate. So right here, this is our 7.707 of our volt peak mark. This is at -3 dB. We could also designate these guys, or we could show them in dB form instead of using the volts. We could use that as well, and that would create more of a linear scale for us. We could also go through and we could plug this into Excel or something and create a chart for us, which I will do later and post that just as by itself to show you guys that here's the chart for it, or maybe I'll tag it to the end of the notes. But either way, you'll still have that because I know this isn't quite drawn to scale. This should be actually pretty close. Where these two cross, they should be actually on this line. So I didn't draw that. I didn't draw this this graph very close to scale. It's just very, very roughened. But the idea here is, at this point where you see this negative 3 dB, this 0.707 of whatever our max voltage, so anything that is above that line, we want to pass those frequencies through without changing at all. If it's below this line, we want to attenuate the signal so it gets down next to nothing. So if you look, underneath this 0.707 volt on our purple line, we see this really sharp steep angle, and then it really quickly levels off. So what this is doing is the resistor, or when we have the output taken across our resistor, we are allowing higher than the 0.707 volts of our max voltage. So anything higher than 3.5 volts, we want to allow through without changing the signal at all. So if we want to allow a higher frequency, which type of filter is that going to be? So in this case, the resistance is going, when we have the output taken across the resistor, this is going to be a high pass filter. Because anything from this point forward, this purple shaded area, those are the frequencies we want to pass. So we're passing high frequencies. Okay. Conversely, when we look at the red line, it has the same trend, but it goes in the opposite direction. It starts out really high, but then once we start getting back around to this critical frequency area, we see this sharp slope fall off of the voltage of our capacitor. So because of that, at high frequencies, we've attenuated the signal. We don't want that. So what we want is the signal that's higher than the 0.707 of our peak, or in this case 3.5 volts. We want all of these frequencies to be going through our filter so we don't affect it at all. So since that, we're using the lower end of the frequencies. That gives us a low pass filter. And so we can see, depending on what frequency we're going to be running at, or we could even decide, hey, I want this to give us, to be able to filter out anything below a certain value. We can design our circuit in such a way that based on these parameters, we can quickly and effectively design a circuit to produce whatever frequency we want, whatever kind of frequency response we got. And so just by using the capacitors, we have the ability to give us a low pass or a high pass filter using the exact same components. The only difference is, where am I taking my output? So it makes it really nice when we're trying to design something and we decide, oh, maybe I want to switch to a high pass. We can actually just flip our components and now it's a high pass filter. We don't have to recalculate anything. We don't have to change anything. And and everything is going to be relating to this critical frequency. Now, the biggest thing that we need to know and remember is, let's calculate what our critical frequency of this filter is. So now that everything's all said and done, we've seen how they work. We want to know at what point do we achieve our filtering? What point is our break point? And that is our critical frequency. So we'll come back over here to our notes. And we have our circuit right here. We'll just kind of reference in the gold. And I'm going to do this in the magenta pink color next to it. So what we want to know is we want to find what is our critical frequency. How do we find it? Actually, I'm just going to put this below it. What is our critical frequency? At what point do we call this a filter? Okay, and what is this frequency that we're going to label this as? So remember, at our critical frequency is when our reactance equals the resistance. So if we come back and we look at our reactive capacitance formula, well, what we want to know is, we would know what the X value is because we have a resistor, so we can solve for it. What we don't know is what frequency this is at. So now we can manipulate this formula. So we're going to multiply both sides by our F, our frequency. We're going to divide both sides by our capacitive reactance. So we end up with the frequency is equal to 1 over 2 pi times the reactance times the capacitor. Now remember, we want this resistance and this reactance to be equal, so we can even swap this guy out for an R to designate what we do know. So the frequency is equal to, where's my eraser, is equal to 1 over 2 pi times the resistance value times our capacitor. So let's plug those values in. So the frequency is equal to 1 over 2 pi. Our resistor was 15 kiloohms, and our capacitor was 176 picofarads. So now, let's punch that into our calculator, and we get times 15,000 and 176, and then picos to the negative 12th. We want to take the reciprocal of that. So this, our critical frequency of these components, is 60.286 kilohertz. So that is the frequency that we've designed this filter to be. So if we come back up and look at our graph that we've made, so now we'll get rid of these just so we can see. So this point right here, and like I said, I drew it off a little bit. So at this point right here where those two cross, that's our critical frequency. And it should be down below here right on this line. So like I said, I screwed that up. But our critical frequency is equal to the 60.286 kilohertz. So that means on either one of these guys, doesn't matter which one we take, we're going to get a negative 3 dB drop, which is going to be about 3.5 volts across our output. On either side, doesn't matter if we use the capacitor or the resistor. That is our critical frequency, the center point of this filter. Anything above that point is considered to be passing. Anything below that point is considered to be rejected. And so that's how we can design specific filters. So kind of going back to the audio, and I'm going to use the radio that we have set up in the back of the class again as an example. The different colored lights that thing has on it, those are actually wired up to filters. So what happens is they've gone through with the audio signals coming in, they filtered out the bass signals, they filtered out the mids, and they filtered out the highs. So anything that was lower than a certain frequency, they would strip everything else down and then send just that data to another set of amplifiers to boost up the signal again. Then they would take a band pass filter, which we haven't talked about yet, to use the middle frequencies, so it would strip everything else out except for the frequencies that they wanted, or the range of frequencies that they wanted, and then that would be sent to an amplifier to amplify those, and then the lights would kick on when they reached a certain value of those. Then they did the same thing with the highs, the high frequencies. They selected just a high pass filter and said at this frequency up, we want these signals. Anything below that, we're going to reject it. So they were able to break up the spectrum of sounds to be able to get these different signals. So now they have 3 distinct signals, 3 distinct patterns of what they're looking for and what they're amplifying. So with the filters, like I said, this is the application of how we use them, because now we can filter out noise. So one of the things that you'll learn is when you get into RF, okay? So, or even just listening to the radio, that dial that you turn to. So if you think about, I'll use my favorite radio station, for example, is Classy 97. Its frequency is 97.3 FM. That's 97.3 megahertz, I believe. I got to double check on that, but I believe that's what it is. But that's the frequency that you're tuning to. So what you've done is now you've set your radio to, and you've tuned it to only pick up a small range of frequencies above 97.3 and a small range of frequencies below 97.3, and everything else is being filtered out to where it can't be amplified and then pushed into the speakers of your car. And so that's the whole idea of these. You can also connect multiple things to a serial line. So let's say you have 4 or 5 tools that are running in a factory. Okay, and what you want to do is you want each one of those tools, and you have them set up that way, that when they finish a specific task, they send out a signal on this line. Well, now, instead of having to have a single line running from every single tool to be able to give you an indicator when it is done or when it is not. Now you can have each one of those signals send a different frequency. And then you can have on the receiving end, so you can have different indicators that, again, just like with the radio station, it's going to filter out every other frequency except for the one you want. So then when it gets a signal, let's say we're sending out on a line that we're sending out a 1 hertz signal, we're sending out a 1000 hertz signal, or even going with this example, a 60 hertz, 6000, 600K, and 60 meg. So each one of those tools is sending out a very different frequency for a voltage. Well, when it comes into the line, you're going to have 4 different filters. One of them is going to be set up for 60 hertz. So when you get one tool that sends in a 60 hertz signal, it's going to see it and go, oh, hey, that's me, blink, and it's going to turn on because it sees that signal. And you're going to filter everything else out. You don't want your circuit that turns on the light to see any of the other signals, because you could have all 4 of them going on all at the exact same time, but you don't want a 600 or a 60 megahertz signal to trip your 60 hertz signal, because then it would be saying, hey, I've got this tool done, but it's really not. You only want the specific frequency. And that's where the power of these filters come into, is now we can take these guys and we can calculate what is a high pass, what is a low pass, what's my frequency. Okay, what if I want to design a certain filter at a frequency because, for whatever reason, I'm trying to isolate that frequency. Maybe we're trying to isolate some noise that's coming in on our line and we want to track it down. So we're going to build a filter that's specifically designed to the frequency of the noise so we can start troubleshooting. Okay, do we have noise here? Nope, there's nothing there. Do we have noise here? Oh, there it is. So we know we can work backward through our system and trace this signal, eliminating everything else other than the signal that we're looking for. So that's kind of the real application and the power of filters. So with that being said, those are kind of the steps on what we want to be looking for when we're solving for filters. At the end of this video, we're a little bit over an hour, and I try to keep them under an hour as best I can. So what we're going to do is I'm going to have 2 circuits to design, and then we will pick these back up and talk with them on the next video when we start talking about RL filters. We'll come back with the design of these guys first thing and solve for them. And then the same with the RLs, I'll leave with some RL designs, and then the next video will pick up where we actually solve for those guys. So the circuits that I have and the designs I want to consider. Number 1, we want to design a circuit to be, let me just clarify this, an RC circuit to be low pass. So there's our first clue. I want my critical frequency to be 20 kilohertz. And using the following parameters. So my critical frequency is 20 kilohertz. So this is the information we're given. The capacitor I want you to use is 0.47 microfarads. And the Vin is equal to 5 volts peak. So basically with this point, I need to know what is my R, and I need to know the configuration. Basically which parts are coming first. So work through that schematic, and like I said, we'll talk about it in the next video as well. Just kind of give you guys some practice and some thought about this. So design an RC circuit, an RC filter. Let me change that. So an RC filter to be low pass and have a critical frequency of 20 kilohertz. So the information that I've been given is this. My critical frequency is 27 kilohertz. I have a capacitor of 0.047 microfarads, and I have a Vin of 5 volts peak. So that's our first one. The second one that I want you guys to think about is, again, we're going to design a filter, but I want to design an RC filter to be high pass. So there's my key there. My critical frequency, I want to be 120 kilohertz. My R value, I want to be 2.2 kilohertz, or 2.2 kilo ohms, sorry. And my voltage in is going to equal 5 volts peak. So like I said, take what we've learned in this example and kind of what we were talking about to go through and solve for these things, work it backwards, solve for the components we need, and again, we need to know what the R value is for the second one and the configuration for it. How is it laid out? And we will talk about that in the next video. Good luck.